Hello and welcome to Section 2.3 on differentiation rules. In Section 2.1, we define the derivative of a function using limits. The aim of Section 2.3 is to simplify our lives and develop rules for differentiation similar to the limit laws and continuity laws. We've begun to explore the derivative as instantaneous rate of change, representing the slope of the tangent line. You will need to recall this concept in your exercises, but the focus of this section will be on calculation. Some derivatives are relatively easy to calculate using the limit definition of a derivative. Take the parabola x squared. We start with the limit definition of the derivative, replacing x plus h for x in x squared, expanding x plus h squared, and canceling x squared. We factor h from the numerator and cancel it. And we're left with a polynomial, so we can use direct substitution to find 2x. The relative ease in which we calculated the derivative of x squared is not typical. Sometimes calculating a derivative through the limit definition can be a nightmare. None of our techniques have yet prepared us to solve this limit. Our goal is to develop rules around these situations. By Section 2.5, you should be able to find the derivative of f, though without worrying about the limit. Our differentiation rules will come in two types. The first type will be the derivatives of the most basic functions, our building blocks, and the second type will be the derivative of function operations. The differentiation rule for composition will be developed in Section 2.5, and we will review composition in Section 1.3. Derivatives for trigonometric functions will be calculated in Section 2.4. But the remainder of the rules will be presented in this video. The ability to decompose functions into their building blocks and function operations is an important skill in calculus. Take, for example, f and g. Pause the video and take a minute to decompose f and g into their basic building blocks and function operations. One possible decomposition of f is into r and s. We can then use the quotient, sum and difference, and constant multiple combinations to construct f from r and s. One possible decomposition for g is into the pieces r, s, and I, where we can use the product, sum and difference, and constant multiple combination to construct g from r, s, and I. We begin with the derivative of building blocks, specifically constants and powers. We can use the limit definition to find the derivative of a function f of x equals c for all x. We can use the limit definition to find the derivative of a constant function f, and no matter what the input, we replace f with c. In canceling the numerator, we find that the derivative of a constant function is 0. It shouldn't be a surprise that we obtain 0, as a constant function has no change. Harder to justify, the power rule holds for any real number n. The derivative of x to the fifth is 5x to the fourth. Using the power rule, the derivative is found by multiplying the exponent by x to an exponent smaller by 1. The power rule holds for roots. Recall that the square root can be written as x to the 1/2. In fact, a root can always be written as a fractional power, therefore the power rule works for 2 of our 3 building blocks. Therefore, the derivative of x to the 1/2 is 1/2 times x to the 1/2 minus 1 power. For the differentiation rules on function combinations, we will be assuming that the derivative for both f and g exist. If one of the functions are not differentiable, then the following rules do not hold. The constant multiple rule says that a derivative can occur either before or after a constant is multiplied. Take, for example, the derivative of 4x squared. We know the derivative of x squared exists, so the 4 factors out before we take the derivative. And using our power rule, we find that the derivative of 4x squared is 8x. Let's take a moment to calculate the summation rule for derivatives. We begin with the limit definition of the derivative and break apart f plus g. We'll then pair up function terms in the numerator and split the fraction. Though we can split the fraction, we might not be able to split the limit. From our limit laws in Section 1.6, the only way we can split a limit over addition is if each individual limit would exist. However, note that the individual limits are the limit definitions for the derivative of f and g. Since we began by assuming that our functions are differentiable, that means the limits exist. So we can split the limit and obtain our new sum rule. We can combine our sum and difference and constant multiple rules to find the derivatives of polynomials. Take, for example, this polynomial. We can split the derivative using both the constant multiple and the sum and difference rules. And we can finish calculating our derivative using the power rule. Cleaning up our equation, we find 9x squared minus 2x plus 4. The product rule is slightly more complicated as a formula than the sum and difference and constant multiple rules. A few minutes ago, we decomposed this function into its building blocks. Notice that the function is a product of a square root, which we'll call f, and a polynomial, which we'll call g. Both are functions which we can differentiate. By writing the square root as x to the 1/2, we can use the power rule to find the derivative of f. We can take the derivative of g using the sum and difference and the constant multiple rule, and we calculate our derivative as f times g prime plus f prime times g. So if we combine the individual pieces, f, g, and their derivatives, the product rule could be quite easy to use. Our final rule for this video, the quotient rule, is even more complicated than the product rule. Fortunately, there is a convenient mnemonic to help you keep the numerator straight. It is read low d high minus high d low, and what is meant by low is the denominator g, and high is the numerator f. When we say d, we mean to take the derivative. So low d high means g times f prime, minus high d low means f times g prime. Let's finish with the last example. Pause and challenge yourself by finding the derivative for this expression. One way to begin is by using the quotient rule. We can call the numerator f and the denominator g. Using the power rule, we find that the derivative of f is 1. And rewriting the square root of x as x to the 1/2, we can use the power rule to find the derivative of g. So attacking this problem directly through the quotient rule leaves an expression which needs to be simplified. Alternatively, we could have rewritten our expression before we took our derivative. By rewriting the square root of x as x to the 1/2, and then performing the division operation, we have an expression for which we don't need the quotient rule. Due to the summation rule, we can use the power rule on both pieces, use arithmetic to clean up a bit. Both approaches are correct. However, the quotient rule was a bit slower in this case. You now have the derivatives of a few building blocks and the ability to differentiate using sums, differences, products, and quotients. In Chapter 3, we will explore the applications of derivatives. Being able to easily take derivatives can surely be the difference between comprehension and confusion. Therefore, it is expected that you will practice these rules until they are second nature.